In this video, we're going to be talking about how the different finance formulas were derived, how their equations were formed. So let's write down the title, Derivations of Finance Formulas. So let's start off with simple interest. As you already learned, you know that the formula for simple interest is amount is equal to principal plus the interest rate, which is principal multiplied by the interest rate multiplied by the time, the amount of interest. So let's write down the amount of money you get after each year on a yearly basis. So for year one, you have your principal plus your interest, the amount of interest that you gain, which is IP, because your interest rate multiplied by the principal gives you the amount of interest you earned that year. Then for year two, you get your principal plus 2IP, because remember that for simple interest, the interest earned is always a constant number. It's always based on the first principal invested. So assuming we have these two numbers for our first 2 years, we can factor out the variable p, the principal, to get p bracket 1 plus, well, let's just write p. But as you can see here that there's a different coefficient, or sorry, that should be I, not p. Just get an eraser. That should be I. So let's just write 1 plus ni, because the n here represents the number of years. So if we go on to p plus 3ip, n would be 3. And if we compare this to this formula, you can see that p is the principal and 1 plus ni is the interest rate, or the interest earned after an n number of years, after say 1 or 2 or 3, or how many number of years you want. So I just factored it out to show you that. Now let's expand it back in. So principal plus p and I, where principal is the initial amount of money invested, n is the number of years that have passed, or the amount of time that has passed, and I is the interest rate. And as you can see, this is very similar to this formula right here, and in fact this can even be rewritten as p plus prt, because I corresponds to r and t corresponds to n. They are essentially the same things represented by different variables. So this is how we get the formula for simple interest. Your final amount after an n amount of years is equal to your principal plus your interest earned. And we've already learned that PRT can be written as P and I. So this is the derivation for a simple interest formula. Let's move on to a compound interest formula. Compound interest. So if you recall, you know that the formula for compound interest is amount is equal to principal multiplied by 1 plus interest rate to the power of n. So again, let's start off by writing the amount of money you have after let's go with 2 years. So at the end of the first year, you have your principal plus IP, your principal plus the interest earned after the first year, which is pretty much the same as your simple interest rate. You can see that P plus IP is common for the first year between compound interest and simple interest. Now let's factor out P for this the first year to get P bracket 1 plus I. And these two are the same thing. This is the amount of money you have after the first year. Now for the second year, you have your principal brackets 1 plus I, because you are starting off with this sum of money at the second year. So that would be your, well, you can't really say it's the principal after the at the second year, but let's just call it that for now. This is your principal at the beginning of the second year plus the interest rate for the beginning of the second year. And as we've learned, the interest rate is calculated on the principal at the beginning of that year. So that will be I bracket P 1 plus I. The interest rate is calculated on this number right here, that number. Now the final amount you have at the end of 2 years can be calculated by adding the interest, or the amount of money you have for the first year by the amount of money you have for the second year. So let's add that up right now. So for that, you get P bracket 1 plus I plus I bracket P bracket 1 plus I. Oh, I wrote I plus 1, but same thing. So you get, well, you're not really adding it up, I guess, per se, but this is the amount of money you have at the end of the second year, which is essentially you're adding up the amount of money you have at the end of the first year and the second year. But for our purpose, let's write it like this. So you have that, and as you can see, the common term between both of these two terms is p bracket 1 plus I. So let's factor that out. So you have p bracket 1 plus I, and let's separate that. It's a new section. So p bracket 1 plus I, and after you factor it out, the term that's left is 1 plus I. That's the term that's left. And this can be simplified to p bracket 1 plus I to the power of 2, which is what you essentially have over here. Whoops. That is what you have over here. Your principal multiplied by 1 plus the interest rate to the power of n. And where n is the number of years or how many ever compounding periods you have. And in our case, it's 2. So that's how the formula for compound interest is derived. So moving on, let's go to the formula for an ordinary annuity. Now this is a tricky sort of formula, so we'll try to go slowly. So formula for ordinary annuity, which, as you may recall, is amount is equal to the payment period, or sorry, payment brackets 1 plus I to the power of n minus 1 divided by I, close bracket. So to get this formula, again, the first thing we have to do is write down the amount of money you get after each period. So in this case, the first return you get upon investment, let's go back on a yearly basis. So the first return you get every year, or at the end of the first year, is R. At the end of the second year, it would be R multiplied by the interest rate based on R. For the second year, R plus interest rate squared. And again, for the third year, you get R plus interest rate cubed. And you can keep going like this until you reach R plus 1 plus interest rate to the power of n minus 1. So why is it, you may ask, why is it n minus 1? Well, the reason is simple. Is because the first value here is at a integer, or say an exponent of 0, because this can be rewritten as 1 plus I to the power of 0. So, and this can be 1. So that's the reason it's n minus 1, because you're starting from 0. So the amount of money you have at the end of all of this, you get by adding up all of these terms to get your final amount. So let's add them up right now. You get R plus R bracket 1 plus I plus R bracket 1 plus I squared, all the way up to R bracket 1 plus I to the power of n minus 1. Now we see a common term between all of these, which is R. So if we factor out R, we can get R bracket 1 plus 1 plus I plus 1 plus I squared, all the way up to 1 plus I to the power of n minus 1. Now I'm going to cheat a little here. I'm going to replace 1 plus I with the variable x. So we're going to say that x is equal to 1 plus I. So let's rewrite that to make it simpler. So you have R 1 plus x squared, all the way up to x to the power of n minus 1. Now if you're shrewd, you may notice here that we have a geometric sequence. There is a common ratio between all of these, and the common ratio here is x. Each term is multiplied by x to get the next term. So if you multiply 1 by x, you get the second term. If you multiply x by x, you get x squared, which is the third term, and so on. So the common ratio is x. And as you will recall, the formula for a geometric series, because that is what we have here. We have all the terms of a geometric sequence added up together. So if we recall correctly, the formula for a geometric series is Sn is equal to A brackets Rn minus 1 divided by R minus 1. So let's look at our A value here. We have, in our geometric series, our A value is, so our A value is R, as you can see from here. So scroll down a bit. So we can replace A with R for that. And as we already established, the common ratio, or R, is X. The common ratio is X. So we can rewrite that as X to the power of N minus 1 divided by X minus 1. Now the next thing to do is to substitute 1 plus I for X. So if we do that, scroll down for a bit, we get R times 1, what's it, 1 plus or 1 minus? 1 plus I to the power of N minus 1 divided by 1 plus I minus 1. And if we expand the denominator, we can cancel out the 1 and the negative 1 to get a final formula of R brackets 1 plus I to the power of N minus 1 divided by I. And as you can see here, this formula is the exact same as the formula for an ordinary annuity, which is R brackets 1 plus I to the power of N minus 1 divided by I, which is exactly what we have here. Now the final formula we have to calculate is the formula for the present value of an ordinary annuity. So the present value, I'm going to shorten that, of an annuity. So as always, we're just going to write down the formula first, and the formula for the present value of an annuity or an ordinary annuity is present value is equal to the monthly payment multiplied by 1 minus 1 plus the interest rate to the power of negative n divided by I. So let's write down the sequence again for the present value of an annuity or an ordinary annuity. So for year 1, you have your monthly or your periodic payment divided by 1 plus I, which is your interest rate or interest. And again, for year 2, you have R divided by 1 plus I squared. Scroll down for a bit here. And for year 3, you have R 1 plus I to the power of 3, all the way up till R brackets 1 plus I to the power of N. So to get your final amount or your actual value that you're looking for, you have to add all of these. So let's do that right now. You have your first term, which is R over 1 plus I plus R over 1 plus I squared plus R 1 plus I cubed all the way up till R 1 plus I to the power of N. And again, we see that we have a common, actually let's represent 1 plus I with X first. So let's say that X is equal to 1 plus I. So we can rewrite this formula as R over X plus R over X squared plus R over X cubed all the way up till R over X to the N. Factor out R from here. So if we factor out R, we get R brackets 1 over X plus 1 over X squared plus 1 over X cubed all the way up till 1 over x to the n, and that simplifies it quite a bit for us. Now if we look at this formula really carefully, we can notice that it's again a geometric sequence, and as we learned before, the formula for a series, not sequence. The formula for a geometric series is, let me just go to it, is Sn equals a, the first term, multiplied by Rn minus 1 divided by R minus 1. So if we substitute our values into that, you get, if we substitute our values into the formula for a geometric series, you get an a value of R, again, multiplied by 1 over x. Actually, let me rewrite the formula. Maybe that'll make it easier to understand. Let me just see if I can copy the formula over. So copy. Doesn't seem to be moving. Okay, I'll just rewrite the formula then. So the formula for a geometric series is Sn is equal to a brackets Rn minus 1 divided by R minus 1. So as already mentioned, the a value here was R, and we can see that the common ratio, the term that you, or the value that you multiply each term by to get the next term, is 1 over x. 1 over x. So I made a little mistake here, so I'm just going to erase that. The mistake I made was that R is not the a value, because if we look at our sequence here, or our series here, we can see that the a value, the first term, is actually 1 over x, and R is just a coefficient. It's outside the series. So I'll just rewrite that formula so that it's correct. Erase, erase, erase. Just bear with me. So R is simply the coefficient. So we have the payment brackets. The a value, as already mentioned, is 1 over x. 1 over x. And we already mentioned that the common ratio was also 1 over x. So 1 over x multiplied by 1 over x to the power of n minus 1 divided by the ratio, again the common ratio, is 1 over x minus 1. Close those brackets. And as you can see here, the numerator and the denominator both have 1 over x, which means that we could potentially factor them out. But the problem here is that this is in two terms. So we'll take this step by step. The first thing I want to do here is to get rid of this fraction, because it's very ugly to me, and I don't really like fractions in my work. So we've learned that when we have a fraction with an exponent, we can rewrite the exponent so that it becomes negative and get rid of the fraction. So we can rewrite that to 1 over x brackets x to the power of negative n, should be brackets around those, minus 1. And next step, we want to separate this and factor out 1 over x. So let's do that. We'll factor out 1 over x, which leaves us 1 minus x when factored. Close those brackets. So now we can cancel this out. We can cancel out this 1 over x and that 1 over x. And this leaves us the formula r brackets x to the negative n minus 1 over 1 minus x. So let's resubstitute our x value here, and as mentioned before, the x value was 1 plus I. So let's resubstitute 1 plus I for x. Oh, I'm running out of space. Wonderful. Let's move it over here. So if we substitute 1 plus I for x, we get r brackets 1 plus I to the negative n minus 1 over 1 minus 1 plus I. And we can see here that we have two terms in the denominator, so let's simplify that. This is a little messy. I'm gonna have to, let me try moving it over a little bit up so that's easier to follow. No. Oh, there we go. So let me just move this up here. There. So let's simplify the denominator. So if we expand that, we get r brackets 1 plus I to the negative n minus 1 over 1 minus 1 minus I, which gives us, obviously, r to the 1 plus I negative n minus 1 divided by negative I. Now, a negative number in the denominator is always ugly. No one likes a negative number in the denominator. So let's change that. So we can rewrite this formula that we have right here, this equation, to equals r brackets 1 minus 1 plus I to the negative n, and this leaves us free to get rid of that, change that negative to a positive. So this becomes positive I. And this is the formula for present value of an ordinary annuity. We can write PV here. Whoops, not a P. So we have present value is equal to the monthly payment multiplied by 1 minus 1 plus I to the negative n divided by I. And there you have it. This, what I just showed you right here, this is how you derive the formulas for all your finance equations. And this is extremely useful if ever in university or in your future careers you are ever asked to do something like this.